Hey everyone. So we're back live streaming. I'm sorry that I didn't do it last week. Basically, it was a long weekend, and so my sense of time was discombobulated. I mean, it always is because I'm a grad student. But uh, yeah, I just basically totally forgot about it until it was Monday, because that was like, relatively speaking, my Sunday. So that's what happened. I've also been meaning to make some bonus videos to say I'm sorry and to make it up to everyone, but I've been too busy to even do that. So I do have to apologize for that. Now, depending on where you are in your individual courses, I know for the linear algebra course I'm TAing, we're coming up on vectors in Rn and applying our things like solving systems of equations and determinants and all that. Now we're talking about like visualizations in Rn. So given that, what I would what I would like to show everyone or remind everyone is to go to 3 Blue, 1 Brown and check out those videos. So this is here are the videos for 3 Blue, 1 Brown. It's the essence of linear algebra series. As you can see, there's like 15 videos here. And I would definitely say, yeah, I mean, now is the key point, right? Because we're taking these abstract mathematical tools from the beginning of the course, like determinants and row operations, and it's like, okay, whatever, we're just like moving symbols around and solving these seemingly arbitrary problems. But the nice thing, I mean, this channel has such beautiful animations. Like you can see if I just click through these different things, there's these nice animations of what's going on, because it turns out that all of this means something, right? Like all these numbers and symbols you're writing down, it has this geometric meaning. And in order to excel at the course, I mean, the key to excelling at this course is understanding that geometric meaning. So, yeah. So that being said, I mean, I guess it's time to get into it. So, maybe I'll go back to here and we'll go to our textbook, and I'll just pull up an example from the textbook, right? So parametric lines. I was getting some questions about these parametric lines. So one way to think about this, so we have our equation for a general line, right? So what's our equation? Hold on, let me see which screen am I sharing right now. Yeah, I want to go back to this. So our general equation for a line is, let's say we have 2 points. I'm going to call the points, this is a little bit different notation than the textbook, but let's say we have 2 points, PQ. Well, let's just think about the two-dimensional case, right? So I think, you're going to be doing stuff in like 3, 4, however many dimensions here. And of course, we can't visualize things above 4 dimensions. And it's pretty hard to draw things in 3 dimensions, right? So like, if you're not used to, drawing like a perspective of like the square, on the plane, like you're not used to doing these sorts of drawings, it can be hard. But I think for a lot of the questions, even though you might get questions that have to do with 3 or 4 dimensions, a lot of these questions, we can draw 2-dimensional pictures, and it will really help our intuition, even drawing those 2-dimensional pictures. So for example, if I draw my plane here, right, let's think about this equation where we have 2 points in the plane. So maybe this is my point P over here, and this is my point Q, right? So if I think about this point in the plane, I've got this line here, and so this is the line L is the line that goes through each of them. And you've probably at this point, you know, if you're following the text for this course or any course for that matter, you've probably seen the equation that there's a vector determined by 2 points, right? So the vector determined by the points P and Q. So we write this in order because we imagine this as the line that goes from P. So it starts at P, it has a tail of P, and it goes to Q. We define this to be the vector whose tip is given by, we take the point Q and we subtract the point P. So to give you a concrete example, you know, maybe over here, this is the point 1, 3. And maybe here we have the point, oh, sorry. That's the point 3. 3 on the x-axis, 1 on the y-axis. And over here, maybe we have the point, which is, this is 1 minus 1. Maybe I should draw that a little bit more symmetric. So here's our point 1 minus 1, right? And so the vector determined by this point, according to our formula, so the vector whose tip is 3, 1, and whose tail is 1 minus 1, according to this definition, we take 3, 1, and we subtract 1 minus 1. And so coordinate-wise, this becomes, well, 3 minus 1 is 2. 1 minus negative 1 is 2. So the vector that represents this, remember, our vectors always start at the origin. So I should perhaps make a separate picture here where we're thinking about where the vector itself lives. So the vector representing the distance between these 2 points, or the arrow going between these 2 points, is this vector here, whose tip is at the point 2, 2. Okay, but here's a question: why? Right? Why are we making this the definition? Right? Like if I have 2 points, why does it make sense to have the tip of the vector representing the difference between them to be Q minus P? Right? Because it's like, you know, your professor tells you that, your teacher tells you that, and you go, okay, yeah, I guess I'll just remember that formula, whatever you say, right? But you should ask why, right? You shouldn't be you shouldn't just sit there and be like, oh, okay, well, yeah, whatever you say, you know, you're smart. I'll just believe you. You should try and engage critically with the material and think, well, why are we doing that? Why isn't it P minus Q? Why isn't it 3 times Q minus 40 billion or something? So here's the idea. Let's say I have my points in R2. And let's consider the grid of points. So again, this is why you should watch 3 Blue 1 Brown's channel, because he's got a lot of great animations. I'm just sort of doing this, you know, off the cuff, unpracticed. You know, I'm just making these raw sort of videos because it's an easy way for me to, you know, try and help all of you more without having to do too much extra prep like my regular sort of videos. So let's consider all the integer points. So what do I mean by that? Like this middle point is 0, 0. This point here is 1, 0. This point here is 2, 0. This is 3, 0. This is 1, 1. This is 2, 1. This is 3, 1, etc. Right? So I'm only considering the points on this grid whose both coordinates, their x coordinate and their y coordinate, is both equal to some integer value. And the only reason I'm doing this is because I want to show you an example of a way of transforming these dots on the grid. And it's just going to be easier if we just focus on these dotted points instead of thinking about like the whole continuous grid here. So I'm going to do, well, this you're going to see later on. This is an example of a linear transformation. So maybe you've already seen the definition of this before in your course. Maybe you haven't. But remember this word and remember what I'm showing you, because I'm going to show you something that's an example of that. So here's what I'm going to do. I'm going to take any point P sitting in the plane. So this means I'm going to do this operation to even like these weird points that like appear anywhere in the middle. But again, just for easier visualization purposes, what I'm just going to apply this to the dots to help you see it. So I'm going to take every single point in the plane and I'm going to transform it to the original point that I started with, but then I'm going to subtract the point 1, 2 from it. So let's see what happens when I do that, right? So for instance, I wonder if I can make a copy here. I probably can. And then just copy this thing below. That would be cool. Yeah, so probably copy and paste. Perfect. So what I'm going to do down here is I'm going to write the where the resulting point goes. Maybe I can even do this on the original grid. So for example, let's start with the point 0, 0, right? So where does this point go? The point 0, 0 becomes the point, according to this rule I'm defining, the point 0, 0 becomes the point 0, 0 minus 1, 2. So in other words, it becomes minus 1, minus 2. So where's that point on our grid? Well, here is minus 1, minus 2. It's down here, right? So the point goes down here. Okay, where does the point, where's the point 0, 1 go? Well, according to my rule, I'm going to take it and I'm going to replace it with the point 0, 1 minus 1, 2. So I'm going to get the point minus 1, minus 1. So that is this point down here, right? This is minus 1, minus 1, and here's the point. Okay, what about the point, let's say the point 2, 1. Where does that go? So it goes to the point, again, according to my rule, it goes to the point minus 1, minus 2. So that's going to be the point 1, minus 1, right? So positive 1, minus 1 down here. And maybe you can start to see this pattern already. Basically, all the points are getting shifted in the exact same direction. So I'm just going to fill in these arrows now. Of course, it's not perfect because I wrote things, I didn't measure things properly with a ruler and measure distances and everything. But you can see all these lines I'm drawing look roughly parallel. And so the point of this is that all of these lines are it's just the same translate. So what this operation does, if I'm taking every point, I'm translating that point by the same amount, right? So another way to think about it is that I'm shifting it by the same sort of vector. So we can imagine I simply take a copy of this line, and so I take a copy of this line, and I just apply it. I just put the tail of it wherever that point is, and wherever the tip of that line shows up, that's where I'm going to put the new point. So notice I'm not twisting my arrow around in circles. I'm not stretching it. I'm not moving it. I'm literally just shifting it up and down, and I can apply this to any single point in the plane. Okay, so now you might be losing focus a little bit and be saying, well, what does this have to do with the original thing, right? We're talking about the vector that defines the difference between these 2 points. So if we think about what would happen if I applied that to these pair of points here, for instance. So what were those points? That was the point 1, minus 1, and the point, what was it, 3, 1? Yeah, so the point 3, 1, right? So this was my, these were the 2 points, and I wanted to express this distance between them, right? So what would happen if, so this is my point 3, 1, and this is my point 1, -1 here. So our vectors, right, when we're thinking about an actual vector and not just a point in the plane, although we represent our vector by the point that represents its tip, normally vectors are always something, we think about them as arrows starting from the origin. So they could have any length, they could point in any direction, but we always think of them as arrows whose tail is at the origin, and whose tip is just some point in the plane, right? And this is true even for 3, 4, 5, however many dimensions. So if we think about what's happening here, then in order to represent this distance between these 2 points as a vector, I need to get something that has its tail at the origin, right? So what I'm going to do is I'm going to apply a transformation. I'm going to take every point, just like I did up above here. And here's the other thing to notice. So remember I took this point, this arrow here, and notice what was happening, right? When I do this translation, right, this translation here, I'm not actually changing the distances between any 2 points, right? Of course, there's a difference between where my point begins and where my point ends. But if I take any 2 points, they're all shifting by the same amount. That is key here. They're all shifting by the same amount. And so if I start with 2 points, even though they both end up somewhere different, the distance between those 2 points originally is the same distance as it was before. So if I apply this transformation to the plane, where hold on, let me make a copy of this down below. So if I apply this transformation, I do the same thing. I do this linear transformation where I take every single point and I subtract from that point the tail, right? 1, 1, -1. Well, let's think about for a second, where does the tail go in this case? If I have this vector, let's compute where the tail goes. Let me just make a black line again here, might make it a little easier to look at. Well, I simply have to compute it, right? So if I want to know where the point P goes, so if here P is the tail, it's 1, -1, then it's going to get set to the point 1, -1, minus 1, -1. But then look what happens. Those are the same points. So this answer is just the point 0, 0. So where this tail ends up after this transformation is the point 0, 0. Where the tip ends up, again, I do the same thing to calculate it. So this is 3, 1, and I subtract from it 1, -1. So this is going to be 3 minus 1 is 4, and 1 minus -1 is 2. So this is going to go to the point 3, 2. Or sorry, to the point 4, 2. So I count over 1, 2, 3. I guess I need to make more points. Hang on a second. Yes, I made a very silly mistake. And hopefully you caught it too. Let me just check the chat. Yeah. So 3 minus 1 is 2. 1 minus -1 is 2. So it actually goes to the point 2, 2. So that is here, right? This is point 2, 2. So this new arrow, right? Actually, it should be passing through this point here. And so this new arrow, what do we know about it? So this new arrow, it has the same length as the original arrow, right? Because I've just shifted everything. The fancy word for this that mathematicians use sometimes is an isometry, So this is a way of shifting all the points that doesn't affect the distances between those points. And so I've shifted it over, right? But now the point is, if I think about this line whose tip is this end point of the point 3, 1, now this defines a vector for me, right? Because all my vectors I'm thinking about is having tails at the origin. And so this is this line segment that has its tail at the origin. But now what's more interesting about this is it has the same size, right? It has the same distance as these 2 points. So sometimes this is called, the norm or the length of the vector, right? So the norm or length is the same as the distance from the original points. And okay, so big whoop, you might be saying, right? So I want to remind you, because it's been a few minutes, what we're trying to do is talk about the equation for a line and why it is what it is. Right? The equation of a line. Did I write it up here? Did I write it out for you yet? Not quite. So we were just talking about rather the vector representing 2 points. So this is why, right? This is why we do the why this vector is represented by the point that we want to be the tip, subtract the point that we want to be the tail, right? Because if I take all the points in the plane and I shift them all over by minus p, that's going to shift it so the tail of my vector is now at the origin, or sorry, the tail of that line segment between these 2 points is now at the origin, which makes it, I guess I need to be careful that my face isn't cutting off the stuff I'm writing. Right, I better make a special box around there or something. So the normal length is the same as the distance from the original points. And so I'm shifting all the points over by p. So what that means is the point q, that I started with up here, right? I know that wherever this ends up, I want this to this is going to be the tip of the vector representing it. So in other words, right, if I want to know if I can describe my vector by the tip that represents it, well, the tip is just going to be the original tip shifted over by p. So that is why we take this as our definition, because we want to make a vector. Vectors are nice to work with. We can do this linear algebra stuff, add them, subtract them, scalar multiply them, talk about distances between vectors, do a bunch of linear algebra and stuff with matrices, right? I want to represent it as a vector. Well, it would be nice if that vector, if it is representing the distance between those 2 points, then the length of that vector better be the length of the original vector, because it should represent that distance between the 2 points. And of course, then it's like, well, what vector do I choose? Well, this is sort of the obvious choice, right? I need to shift that tail over so it's at the origin to make it a vector. So I shift everything. So this is basically what it has to be, right? Okay, but we want to talk about, our main interest is the equation of a line. So the equation of a line, in general, for if I have my 2 points p and q, so maybe I'll write it out as this vector x. So it's, I take my point p and I add to it t times q minus p, for example. And let me just check the textbook convention. Yeah. So there's a slight there's different ways we could do it with different conventions, but and so why would this be the case? Why would this be the case, right? So let me scroll back up to our original picture. So we started with these points here, P and Q. Was this the original ones we looked at, or rather, sorry, this is our point P here, and this is our point Q. So let me erase these other ones here, because this is the one that we're really interested in. These are the points P and Q that we started with. And we want to describe, right, in the plane, if you draw any 2 points, there's a unique line that passes through 2 of them, right? It's just a straight line through those 2 points. And that's exactly what happens in any number of dimensions. It's the same story, right? So there's a line and only one line passing through both of these points, right? So this is our line L that we want to draw. So how should we express this as an equation, right? Well, I don't know how long none of this has been on screen for. My screen went black. I hope it didn't go black when I started showing the 3 blue 1 brown video. I don't think so, because I've been here for a while, and I was checking the chat and looking at the screen. Wow, I really need to get my stuff together if I want more people to watch these videos. I'm going to keep going, and then I guess I'll just delete everything if it turns out that my screen has been pitch black for a while. This is why I need people in the chat to tell me when this is happening. Okay, so getting back to the story, though. So we have our line now, right? My other points on the line, right? I can either like stretch this little blue arrow and I'm going to hit one of those, or I can flip it in the opposite direction, or maybe I could even shrink it, right? If there's this point that's between P and Q, I could like shrink the arrow, right? So the point is that accounts for all of my points, right? I don't need to like make an arrow that twists off and go in some other direction. It's only stretching it or shrinking it, right? So if I think about what does that happen? What does that mean in terms of my vector, right? So I got my vector equation down here, right? And if we think about how everything up here, right, when we translate it, remember, it's not the distance, even though the points end up in different spots, the distance between any 2 points we started with is going to be the same when we shift them both over. So what's going to happen if I'm looking at like versions of this line, ooh, shouldn't have done that. If I'm looking at versions of this line, are like direction, right? And hopefully at this point you've already seen that a vector, right? If we simply take some vector v and we think about the arrow that it represents, multiplying v by a scalar, it's not going to make the arrow point in a different direction. It's just going to make it longer, or it's going to make it shorter, depending on whether this number is greater than 1 or less than 1. Those are the 2 cases. So we're thinking about, we want to try and come up with this equation that represents our line L, and we've realized now that all we really need to do is take into account all of this stretching and shrinking, right? So the vector from P, the point P, to any other point on this line is simply going to be a scalar multiple of the vector for Q minus P, right? So we've realized, right, the vector representing the distance from P to any other point on the line is Q minus P. Well, it's just going to be some scalar multiple of these points, right? And it's going to be any scalar multiple, right? So we could choose any real number, and again, that's just going to over here in like the vector version, multiplying by any real number is just either going to stretch this line or it's going to shrink this line, right? But that's not all the points in our, that doesn't give us the actual coordinates for the points on our line. We want to know the actual coordinates of the point. This vector here is just the distance vector, as we figured out, right? So for any point, there's going to be some number t that we can multiply q minus p by to represent that distance between p and some other point on the line. But we've shifted, right? We've shifted to the origin. So if I make maybe I should just use this picture up here, right? We've shifted this to the origin. So if I multiply this t, right, I'm going to get some like longer line or some shorter line or maybe a line going in the other direction, something like that. What I need to do is get back to my original line, right? My original line was down here. It was passing through these points. Well, what did I do to get my vector through the origin? I shifted everything by 1 minus 1, right? I shifted everything over this way by subtracting by the point P. So in order to get my line back, I just need to do the opposite. I need to replace P. So I just add P to everything, and that will shift everything back. So the equation of the line is x equal to p plus t q minus p. And that's exactly, what you see in your textbook for the definition of the equation of the line. But my hope is that with today's video, I've given you a better idea as to why that is true, right? So you should always be asking yourself, why is it true? Why is the professor telling me, like if you don't get it, look into it, try and question it, try and figure out like, oh, why do we represent, Google it, Google the question, why is this the equation that we use for the line? So hopefully my mad unplanned ramblings have given you a better idea of why this is true. If you want to see more worked examples from me, let me know in the chat. Leave a comment and say, hey, I want to see next week, I want to see more examples of this, or I want to see more examples of that. And I'm not saying I will have the time, but I'm going to try and make some bonus videos. So if there's particular kinds of problems you want to see, maybe those are videos I'll make. I'll make those the topic of my bonus videos. Anyways, that's all for now. That's all for this week, and hopefully I'll see you soon.